Okay, I think we are ready to go. Okay, so should we start? Let me put this a little bit up. It's going to be in the way as we put in pictures. Okay, so a little bit of an introduction. My name is Arnava Majumdar, popularly known as Ron, and everyone calls me Ron, so just call me Ron. And so I lead Center for Advanced Studies for Chicago. Center for Advanced Studies is a group inside of IBM. We work with universities and try to do research and work with students and faculty and see where we can go, right? So we're not in the commercial business so much as helping develop open source and doing work with universities and academia, right? So you can learn a little bit more about myself, get in touch with me on LinkedIn. So we have a full agenda today for this presentation. So we'll start with how the idea evolved, what I now call cognitive telescope network. So it started as like most ideas start with a conversation I had with a professor at Northwestern University, Shane Larson. He happened to be a researcher at LIGO. If you know LIGO, LIGO is Laser Interferometer Gravitational Observatory. We have two LIGOs in the US, in Washington and Louisiana. And I'll show you some more pictures. So we'll start with that whole concept of why we even got started with this whole idea of having a network of telescopes, right? And at the time, I was thinking about doing some experiments with students at the STEM level, at high school or maybe middle school as well, to do interpolation of objects in the sky, getting distances between them, and all that stuff. Some fun stuff, nothing great. But the buildings here in downtown, which I thought would be really, really inviting to the idea of having telescopes on top of their buildings, we're not that much interested. So that idea sort of subsided until my discussion with Shane. And Shane said, hey, this is great. We're doing gravitational observations and with LIGO, but we can't see anything at that time in the sky. So what if we can combine this idea of listening for gravitational waves and take some pictures in the sky with a network of telescopes? Okay, that's a great idea. Maybe it's time to revive my whole idea of telescopes. So I'll go through a little bit of that, show you how the architecture of the network and all this is. And then I'll talk about a very important subject which people usually ignore. It's about safety of telescopes. So telescopes are usually dumb instruments. They have no intelligence built into it, and wherever you want to move it, it'll move, and it can actually crash into itself. So there's some considerations you have to do when you're controlling remotely, right? You're not standing in front of the telescope to press the emergency stop button, right? And taking very precise. These are very expensive instruments. So I'll discuss a little bit about that. And I think I went back. Okay. So controlling telescopes from the cloud. So this is where the Internet of Telescopes comes in, right? So how do we control all these telescopes all across the world from our cloud devices, right? So someone who's logging into an application on the cloud, how do we actually address a telescope and move it, right? And take some pictures and send it back to us, right? And then I'll talk a little bit about some of the artificial intelligence and stuff we are trying to do, how to enhance the user experience to working with a network like this. And the idea is if we can do something with this astronomy, we can probably do it in other domains as well, right? So there's some commonalities and things I'll point out. Okay, evolution of the thought. Okay, so this again starts with gravitational waves, and so there's I wouldn't go through the whole history. You can read it later on. I'll share all the slides and information with you. So and this is Shane Larson, by the way. So this is Shane with his own telescope. and he is part of the LIGO team. Plus he's a professor at Northwestern and so on. Anyway, there's a whole idea of how we can nominate like NBC stars and all that stuff. There was a whole a period of time where people were trying to see how they can notate stars and put it into some database, right? And then something interesting happened. So Einstein predicted that gravitational waves may be possible, and then he had another paper that he contradicted himself, saying that, oh, maybe it's not possible, and so on and so forth. So that led into this whole investigation into black holes, whether we can actually generate gravitational waves or not. So this is a simulation that was done. This is before the first gravitational wave was ever detected in 2016, right? So you can see two gravitational, it's a binary gravitational system. They're going around each other, and eventually they're going to crash into each other and merge, and that's when the gravitational wave starts. Okay. I think this is a fascinating simulation. So you'll see as they come closer, the time will slow down in the simulation, and then the merge happens.
Average time will all be sucked into a black hole.
Right?
Yeah, that is a discussion we were having with Cynthia, right? So entropy is increasing and increasing, and eventually everything's going to evaporate. And also that led us into the discussion with Stephen Hawking's evaporation of black holes, right? So where does the information go, the information loss problem, and so on. So yeah, so as they merge into one black hole, there's a huge amount of ripple that is sent out. Okay, great. Now, where do we go from there? So LIGO is the US-based gravitational observatory. It's nothing but an interferometer. So if you're if you don't know what an interferometer is, it's a very simple system. It has two legs, and there's a laser beam that is split, and it goes down to two of the beams and gets reflected back. So when the light comes back, you check whether they're in phase or they're not in phase. If they're not in phase, then something has happened, which means a gravitational wave must have gone through space-time. How else would the light not meet at the same time? Because it's split on phase, it should come back on phase, right? So if it is not coming back in phase, that means that there's a wave which has. So think about a gravitational wave. So it's a ripple in space-time. Like if you throw a stone in the water, there's ripples, right? So if you think about the cross section, one side will be extended, the other side will be shortened a little bit, right? If it's perfectly at a right angle, right? So that creates the little out of phase, which is how gravitational wave is detected, right? And LIGO is the ground-based system that US has. There's other systems. LISA is very interesting. It's going to go out in 2034, I believe. And hopefully they're still on time. I haven't checked recently. But that's going to be in the sky, so with 3 satellite systems going around the Earth.
So is LIGO the only one that's operating today?
No, there are several systems. So LIGO is definitely operational. There's a system from the ESA, the European Space Agency, that's also operational. So they have one. The interesting thing about LIGO is they have 2 of them. So you see these huge arms, right? So the light is split from here, goes there, and reflects back. So these are 4 kilometers long, and that's when the in phase or out of phase problem happens. But the problem is very, very difficult to actually engineer, because there's vibrations always on Earth, right? So there can be little tectonic movements, a truck goes by, there's little vibration, right? And so on and so forth. So it's a very big undertaking actually. So Livingstone, Louisiana, and Washington. So now we can actually confirm that this actually happened. Because if one of the detectors detects it, right? Well, we may or may not have a gravitational wave. But if both of them detects it, and the distance between them can be calculated, and the gravitational wave goes at approximately the speed of light, so that can be calculated and seen whether, oh, okay, now this wave struck one of the observatories, and then it went past the other observatory. So now it can be really confirmed, right? So with one, you can kind of predict, but you cannot confirm, right? And then you have the space agency. Now, this lists all the projects that are going on currently, right? Leading up to 2034, sorry, for LISA, which will be a gravitational observatory in the sky. Right, so what happened was, okay, so they detected a gravitational wave coming somewhat in this area, right? So that was GW 150914. So 14 is when they detected it for the first time. So it came somewhere in this area. So we don't know exactly where it came, so you can't pinpoint it until you have some visual observations and things like that, right? So that led into the whole idea of having the network in the first place, right? So can we actually place multiple telescopes in this area and take pictures while this happens? So if we can take pictures from gravitational waves, we can probably take pictures of supernovas and other things which are transient. So that's the whole idea. So this network is for transient follow-up of events, right? So what are transient events? Anything that happens in the sky and then it's gone after a while, right? So supernova, gamma ray burst, or anything like that, right? So for all these use cases, we can use a similar network. So this is a brainstorming session we had. I just kept it in there so people can take a look how we derived at that those things. Some analysis, design thinking sessions. And this is kind of interesting because this actually shows how we've broken down the projects, right? So you see at the very top I have open assets. So open because all of this is meant to be open source and anyone should be able to use it. Currently we haven't actually, don't have a public repository on GitHub, but it's on the public GitHub, so anyone who's interested, we can add them to it, right? So until it's a stable system and then we can open source, anyone can download and play with it, right?
Just have to press the button.
End meeting, why? You're already in the meeting, right? Meeting is started. I don't know why. Yeah, I usually get that when the meeting is not started, right? When the meeting is already started, we're already in the meeting. Anyway, so after all this brainstorming, we came up with these modules. So I was showing how we broke it down. So we identified certain hills and then sub-hills and then components and so on. So this event consumer here, you can see it's meant to consume events, and then it's going to pass it on to the observing director module over here, and all the communication is through APIs. APIs are basically REST APIs, which are on. That's how most things are intercommunicating these days, right? So the SOAP days are over. Now we're just doing simple REST API calls between each other, right? So so this also does REST APIs. That's how you communicate between the different modules. Observing director is the guy who's like an observing director at observing station, right? So he takes a decision what images to take, which telescopes to point where, and so on. So this does it automatically. So I'll come to the logic a little bit later, but you can filter out telescopes. Say you have thousands of telescopes in your network, which we don't right now, but imagine at some point when we have thousands of telescopes, you have to find out where the location of that observation is, right? So only few telescopes will be able to point there. Within those few telescopes, there will be weather conditions and all that stuff. And then you have equipments, right? So certain telescopes are equipped with certain filters. certain other telescopes might not be. So there's a whole filtration process, and you come up with these small amount of telescopes which can now be put into a grid formation, which we are calling pilot. Okay? And there you can see it's a collaboration between multiple universities have already contributed.
How many telescopes are you talking about adding? And this is sort of as a supplement to LIGO, correct?
Yeah, so potentially infinite number of telescopes you can add to the system, right? It's a matter of scaling the system, right?
Now, these are optical telescopes.
Yeah, these are all optical telescopes we're talking about.
And so what's the minimum, if it's a reflecting telescope, what's the minimum mirror size that's practical?
If you're talking about a reflecting telescope, so 8 inches, 16 inches can take pretty good pictures actually. So we're not talking about large, huge telescopes, because one of the reasons is, like say the Keck telescope, right? You'll never have access to that telescope. It's always going to be scheduled for doing stuff. But what we're targeting is sub-meter telescopes that people can contribute to this. And a lot of universities have sub-meter telescopes. A lot of individuals, since telescope prices have come down, a lot of people have a lot of telescopes, right? And even with a DSLR, if you take like 300, 400 pictures, you can take pretty good pictures of nebula now, right? The technology has improved, plus the error correction technology has improved.
An 8-inch telescope, yeah, that's somebody with enough money can afford to buy that as an individual. Do you have any ballpark for the cost of that? Is that $10,000?
Oh, no. You can get 8-inch telescopes for probably 2,000, fully automated. The prices have come down really. So that is why you have so much glass on the ground already. Why not use all the glass and use it for the purpose of science, right? So things are not very expensive at all.
What's the payload size of these? How much amount of data they are getting in and you're transferring?
How much data is being transferred? It's a matter of just, so we haven't come across any issues because we don't have so many telescopes right now. But see, the thing is, you have multiple things here. I don't think this particular picture shows cloud object storage. So you're not sending the images directly through the MQTT system, which is the IoT system. The IoT will be overloaded with large pictures, right? So the pictures you're taking are raw images from telescopes, and they're preferably in a format called FITS, F-I-T-S, which is the NASA format for interchange of images between organizations, right? So it's a standard format. So you have some headers.
Each one of the telescope which is automated, it has built the API connection with that and able to.
Yeah. So how do you automate the telescope? I'll come to that. So there's so you have a telescope. To move the telescope, you have a mount, right? So that mount is preferably an equatorial mount. So you're moving with respect to the Earth, right? So the Earth is moving west to east. So the mount is compensating east to west, right? So it's going in the opposite direction to be able to point to the same thing. Now, that is in theory, most mounts will have some errors as well. So over a period of time, if you're taking pictures, you have to recalibrate because it's gonna, the more expensive the mount is, obviously it's gonna stay focused in that one location for a longer period of time, but you have to recalibrate from time to time. So the mount is important. So you have to address the mount. Now, how is the mount attacked? How do you address a mount through an automated system, right? So basically, it'll have a remote control on the side, right, where you can punch in buttons, this direction, that direction, or go right, go left, go up, right? So from that, you have a cable that connects up, and you can have a USB interface, right? So if you don't have a USB interface, they're signal converters. Basically, you have a serial connection coming out of the telescope itself, physical connection, right? So that needs to be converted into whatever programs and send out, right? So how do we do that? So there's something called, there used to be something called ASCOM, Astronomical Common Object Model. So COM is like Microsoft COM, that's where the name comes from. So ASCOM was a protocol to convert them into a common format, right? So you can address that. So ASCOM will have its own server, and you can have a client to connect to that server. Now it's all TCP connections, right? So you have a server socket and you have a client socket, right? So that's how you transfer the data, right? Good.
I got a different question. I got a people question. So
Yeah.
I'm just curious. What caused these 6 universities to come together, and what was it that they looked for from IBM Watson that maybe they couldn't do individually? Like, what was their draw to participate in this, and what was the problem that you all were trying to collectively solve?
Yeah, so
How
these
did-
things, yeah,
how
yeah.
did each one contribute to that? I'm just
Yeah, so
curious.
these things grow organically, right? For my projects, right? So what happens is, so the whole platform, the code development idea, I created that whole platform itself, right? So that multiple universities can actually take up any of the modules, right? So you see all these big blocks, right? Say the telescope commander module, right? So this is broken down. It's how you do the project, right? Basically, it's project management. So that component itself is broken down into submodules or iterations of those submodules or iterations of the module, right? So now I have to see which university is interested, right? So I'm driving it rather than universities coming together. So it's not a university initiative as such, but it's an initiative that we started, and then we're talking to universities. And the thing is, like, all these things are being done through mostly undergrad programs, some graduate programs. This, we didn't have a PhD, but it can potentially if there's some algorithms to be developed, right? So if we have faculty or students who are interested in joining us, we can get them into the program, right?
Is the ultimate, and maybe this is coming up in the future slide, is the ultimate objective for this, for IBM Watson to then maybe commercialize this as a service or offer for IBM? I mean,
Well, that is neither IBM's objective right now, neither it is mine, right? So my, I just am curious in solving problems, right? So, and give it out as open source. Now, if IBM wants to actually create a product out of it, yeah, they're in the same boat like anyone else. They can take the open source and create a product, right?
it is under an open source.
Yes, yes,
that
it is contributing to open source. And that relieves the whole so if you think like having a collaboration with, say, Western Sydney University, NC State, and Northwestern, you'll fight the legal IP issue forever. You'll never get anything done, right? So that is the practicality of the problem, right? So forget about IBM. Now IBM comes into the picture. We're like, oh, okay, let's talk about IP. So does IBM own the IP or Northwestern or NC State? I mean, everyone wants to hold on to IP. Nothing will ever get done. So the only solution that works is open source. Universities like contributing to open source. IBM obviously has a history behind open source, right? And it works for me because I don't care who creates a product out of it. Let's solve the problem first, right? Or else nothing will ever get done.
Very cool.
So
It certainly gives IBM relationships and visibilities into the academic community across the country or across the world.
exactly, and that's why we have the academic program, right? So it is to connect with academia. We give them free cloud credits. How will this work without having a hosting environment, right? So someone has to pay for all these blobs over here on the cloud, right? So our department, what we do is we give free cloud credits to universities, onboard the universities. So if the university and the project is onboarded, we have a bunch of resources, and then, yeah, that's how these things work. And not just this project, like the brain aneurysm project, or say prosthetics project, or whatever I'm involved in. all of them have the same model, right? Open source, free cloud credits, and then whichever university is involved will see how that program works. Some say NC State electrical department does senior design projects for 1 semester. Their computer science does it for 1 semester. Their electrical does it for 2 semesters. So they call it senior design. Now Western Sydney has a whole different program. Macquarie University has a whole different program, right? So you have to marry the two together so that you can scope it out for that particular iteration, for that particular semester or 2 semester long or whatever it is, right? And yeah.
Ron, then the business purpose behind this is really to promote the resources of the IBM cloud.
Yes, so IBM's interest is...
to get very back to the economic basis for doing this.
Yes, so...
That's where this is coming from, and I saw that you were using IBM proprietary IoT frameworks, is that?
Yeah, so what's an IoT? So this thing in the middle, right? Where's my cursor here? This thing in the middle, right? This is what's an IoT platform, right? So that's because we're IBM, we're hosting it, right? We will obviously use our platform, right? That's what we can give out for free also. We cannot give someone else's stuff for free. API Connect, that's another product of ours, right? You'll see all IBM hallmarks all over the place, right? Language translator. Does Google have a translator? Yes, but you can't give their translator for free. You can only provide ours for free, right? And things like that. So yes, it definitely will have hallmarks of IBM. But how are we connecting to Watson? We're not actually trying to use Watson's API. We're trying to use Pavo, for instance. So Pavo, if you know, it's an Eclipse open source project, and it's a free library, right? That anyone can connect. So if someone wants to connect to a different IoT network, yeah, they're more than welcome to do so. Or they can always change the interface, right? Some capabilities will be there, some may not be there, but we try to make it as open as possible, but obviously our stuff is always IBM, right? So. Okay, moving on. Okay. Okay, so this is kind of shows the map of how things work out. So we usually have, this is Slack actually, right? So Slack, we have open communication going on with different, I don't know why it's complaining about, this is continuing, right? Okay, so yeah, different, and we assign a mentor to work with the students. So these are some of the mentors who have already worked on this particular project. So you cannot just let the student do whatever and then it will not be compatible with the next iteration, right? That's one of the reasons. Another reason is it's also a learning experience for the students, right? So we want to train them and see how they can perform. Okay, so we started off with the gravitational waves. Obviously, that's one of the use cases, but it can be also used for supernovas, gamma ray bursts, variable stars, and so on, right? So you can take any of these transient phenomena, including like shooting stars, right? But they're not as interesting as gamma ray bursts, so probably they'll be at a very low priority. So you can use it basically for any of these transient phenomena. Right? Safety of telescopes. So this is actually, I kept it in there because Illinois Institute of Technology actually designed this. And I thought it was a very cool design for having an observatory, right? I think you'll agree. It's nice. There's some problems with the functionality of it. In this particular model, so it has changed, evolved over a period of time. But design actually exists if someone wants to implement it in in reality, right? So it came out of a request from alumni who wanted to create an observatory in Arizona. Didn't actually happen, but that's how they got involved. Okay, so as you know, these are refractive telescopes. How it works, it's just you have an eyepiece, the light comes in and you take pictures. Then you have Newtonian, which is reflective, right? The mirror inside, and then you have a place where all the light is concentrated, right? And you take pictures. So all these telescopes, if you look at it, even some of the larger ones here, the problem is they don't have any mechanism of protecting itself. So it can turn around. If I give a bad, say, RA tag, right? It's pointing here. It can point downwards, and it can break itself, right? And it's a very big problem with telescopes. So it's not something that people talk about because people are controlling it right next to the telescope. But if you're remotely controlling it, you have no idea what's in front of the telescope, how the telescope is moving. You just send a coordinate, and it can destroy itself. So it's a big problem when you're dealing with remote telescopes. So what we're doing is we're actually addressing all these points, right? So the telescope has to move precisely. So if I give a coordinate, so I mentioned ASCOM. ASCOM is kind of going away. The new protocol is called Indigo. So Indy is the new protocol, and that's the server and the client that I was describing for ASCOM actually. Same thing, just different protocol, and much better, much easier to handle. So Indigo, if you give a direction, it'll just go around. But what you can do is move the telescope very, very diligently, right? One step at a time and check. So every time you're moving, and you can control the telescope, the speed of the movement of the telescope. So if I say, okay, I want to go to this point as quickly as possible, yeah, it can go there, but you don't know if it's going to hit something, right? So you can slowly accelerate, decelerate, and it's totally within our control to be able to do that, okay? And that way, if we can mark certain areas as no-go zones, see there's some obstruction here, right, here and here. So what are these obstructions? If you think about it, it's on a mount, right? There's a very, very simple obstruction scenario where you have three poles of the three tripods you put the telescope on. Now, if it's going to move here, it's going to hit the stand itself, right? So those are the no-go zones, and we can control the movement of the telescope to avoid these no-go zones. So that's a critical piece in this, actually. Another thing is orientation of the telescope, right? So yes, it can be manually adjusted and all that stuff, but obviously you're controlling it remotely. Second of all, you don't want to take a lot of time adjusting. So there's something called astrometry, and you can have libraries that can actually detect what these stars are. So you take a picture. So this is Orion, right? Yeah, the Orion's belt. And then it detects what these stars are, and it'll give you exact coordinates of the known objects in the sky. And based on that, it can be aligned automatically, rather than having to do it manually, looking at a pole star, and then calibrating and all that stuff. So, okay. Now, so this is the other thing I was talking about, right? Indy. So we have moved from ASCOM to Indy now. So Indy is similarly a server. So you have so Indy was the first server. Now we've moved on to something called Indigo. So forget about all the old stuff. We don't deal with the old stuff. As things evolve, we keep on evolving. So Indigo server is basically connected to the telescope, right? So how would it connect to the telescope? Again, you have a physical wire, you have a serial communication, and every telescope can have an Indy compatible driver, or else you'll have to write it right. So now what's happening is I don't have to deal with the exact signals that are coming out of the telescope through a serial port, I have a driver that can translate that into what I call the Indigo server, and then all I need to do is my application here can communicate through TCP, simple TCP. So you have a server socket I can write to, right? And I can send an XML object or a JSON object, right? And that's how the whole thing works. Okay? This is critical. This little diagram is critical, how the telescope is actually moving. This is one of the teams we are working with. This is the top IIT telescope at IIT, Illinois Tech, you can see, at the Pritzker Science Center. So we do a lot of experiments with this telescope, moving it here and there, hopefully not breaking it. Right? So that's the objective, right?
Wow.
Okay. So now that we can control telescopes from a ground station autonomously, how can we actually control it over the internet, right? So say a telescope is sitting in Australia, right, Brisbane or whatever. Now I'm sitting here in Chicago. I would like that telescope in the southern hemisphere to point to a certain star, right? So I have to send the signal somehow. So what we've done is we've used the Internet of Things platform, which is the Watson Internet of Things platform basically, on the cloud. It can be anything else. And we're sending MQTT messages. What are MQTT? MQ, teleportation and transportation, right? That's what the full form is. It came out of IBM, that's why it's called MQ in the first place. But anyways, so it's an open standard, I'll come to that you can address, like controlling lights here. If I want to remotely control this light, if it can be controlled through Internet of Things, right? Now you have bulbs that are coming connected to, that's the protocol everyone is using, MQTT, okay? And I will get into a little more details on that. So what does the Internet of Things platform in IBM does? It just doesn't provide a broker. You can also, it's obviously responsive, scalable, and all that. You have device management capabilities, you have some secure connectivity, you have data lifecycle, and all that stuff is built into the platform itself, right? And so you can send messages from all over the place, and then you can reliably process the data on the cloud. Okay? So essentially, what's happening is your telescope, each of these telescopes are basically devices. So like if you have sensors all over this area, each of the sensors is a device in the IoT network, right? So here, each telescope is becoming a device in the IoT network. Okay? And this is a MQTT protocol itself. So Oasis is an open body and actually owns this standard. And you can see they're in version 5, I believe. Yeah, version 5, 5 point something, and that's the latest version for MQTT. And so you can you don't have to use the Watson platform. You can use anything that's compatible with MQTT protocol, and there's a MQTT org as well, which links to Oasis standard as well. Okay. And what we're doing, again, is powerful libraries, which is, again, totally open. Okay. So what is MQTT protocol doing? So you have a broker in between. You have devices on each side, and you can either subscribe to the data or publish data. So it's a pub/sub engine. Okay. So say you have devices here, it's sending information. So that's basically publication to a particular topic that someone else is interested in. So this is kind of totally isolating the sender and the receiver, and it's a many-to-many relationship. So you can keep on adding different sensors or devices, I'll say, on one side that publishes things, and other devices or services or anything can actually subscribe to it. Okay? It doesn't have to be devices, right? It can be my laptop sending a message and another person's laptop receiving that message, right? So the protocol has nothing to do with devices, but it's very efficient in sending small amounts of data. That's why become sort of a standard for the IoT platform.
So this MQTT is proprietary to IBM?
No. Well, everything has origins in IBM.
Right.
So MQTT protocol was originally created by IBM, and the reason it's called MQTT because IBM MQ, right, is a product, right?
Right.
So that product team actually created this and then open sourced it, right? So it is open
So
source
message queuing is being used, that we.
for forever, right?
Mainframe days,
Yes.
right?
Yeah, mainframe. So every bank is using
But
MQ
the whole
behind the
idea of
scenes.
using asynchronous communication, which is
Yeah.
what message queuing is the way that all the communications in this IoT cloud
Yeah.
are moving back and forth.
So if you're familiar with MQ, right? So MQ is queue to peak. You have a source queue and a destination queue, right? It's a one-to-one communication mechanism, right? Then IBM came up with the PubSub model itself on top of MQ. So we had a MQ broker sitting on top of MQ before even MQTT came up. So that's MQ protocol. That's completely proprietary. IBM only knows the exact. Well, you can sniff the network and know how the packets are moving. But that's not to say it's open, right? So it's not an open network. But MQTT is meant for small messages going for PubSub mechanism, right? Only PubSub. So yes, you can definitely have one publisher and one subscriber. So it's simulating like a point-to-point, but it's still going through a publication system, right? So yeah.
So if you were to compare it, can we say it's similar to like Kafka?
Yeah. So Kafka uses a protocol called AMQP.
Okay.
So it's a slightly different protocol. I don't know why IBM also had some source in creation of the protocol itself, AMQP. I don't know why they came up with another protocol. It's a slightly different protocol than this protocol. So it's different at a protocol level. And Kafka, yeah, Apache Kafka, right?
Right.
So totally open source. The protocol is also open source, but it's different. The packets are different.
The packages are different, but
Yeah.
it's also doing the same event-based.
Exactly same thing. Kafka is a PubSub engine, so is MQTT broker. It's exactly similar. So is MQ, but MQ is a proprietary, right? But MQTT and AMQP, they're all similar protocols. So Kafka is using that. Any questions before we move on? Okay. So this is basically a reference architecture. You can find it on the IBM site actually. We have an architecture center. So if you go to this link on the top, IoT architecture, you'll see that. Basically, this is a very common architecture. There's nothing really very fascinating thing about it. Okay. So continuing. Okay. Nothing extremely fascinating about this. It just says you have omni-channel is different channels of communication, right? So you have browsers, iPhones, Android, Eclipse. Eclipse is a development tool where. So you have the telescope commander here in the middle, which is communicating through some IoT gateway, right? So this we're calling the proximity network because this is on-prem, right? So one of the things is how do you deal with? I'll come to some more detailed diagram actually, but how do you deal with communication that fails, right? So one of the problems with telescopes is it can be in remote places where you don't have reliable connections. So connections can fail. You're in the process of sending something. You're in the process of communicating. It fails. So you have to take care of those situations. So we actually have queues in there, MQs. So synchronously they can be sent, right? You don't miss information. So anyway, so what's in the premises that's considered to be your proximity network, and then obviously you get to the public cloud, right? So that's where the IoT framework is, and so on. So this architecture diagram is actually totally independent of any product, right? Hopefully, I didn't mention anything there. So yeah. but it can be applied to with any sort of, right? So what is exactly happening, right? This is a little more details on what's happening. So this is the cloud side, and this is your on-prem side, right? So I mentioned ASCOM server. This is the same as the Indigo server, different protocols. So we are using Indigo now. So this is your IITP server on the cloud, okay? And from the UI, we have an API that communicates with the IoT for publish and subscribe, sends a message over to the device, which is subscribers here, and then it goes to the protection routine, then it goes to the Indigo client, goes up and moves the telescope, okay? For some reason, we have multiple ways of doing the same thing. So you'll see Swift over there, right? So there's a team who's working on Swift, writing very similar code as in Python. We've actually moved on from Python to Java now for various issues and stuff. We'll take that offline. There's a lot of issues we faced with even libraries being supported. So one of the problems with open source is
old is new again. What's old is new again.
Yeah, so if you think about Python, right? Yeah, Java is a full-fledged language, right?
Right.
Python is great, but when you do very complex stuff in Python code itself, it's not the greatest, right? So most of the libraries are, especially a lot of the machine learning and all these libraries are in Python first, and then it goes to other libraries. And why is that so efficient? Because it's written in C, right? You have a thin layer of Python which is calling a C module, which is actually very efficient, right? So if you write the whole thing in Python, it's going to be really slow, right? And it'll have problems, right? So again, that's not the primary reason. The primary reason was support. So open source communities are not really supporting. They publish something, and then these guys in Europe, they just had lots of communication with these guys. They said, oh, well, yeah, we see there's a problem, but we have no time to fix it. I said, okay, so how are we going to deal with it? And then eventually we are going pure Java now. We're going to write to the wire purely with a Java client. We're creating the client right now. Okay, so because this is a key issue with reliability of the system, because it keeps on breaking because of the libraries. Okay, so anyway, so there's a communication and goes to the Indigo server, and then you can move your telescope, you can take pictures, and so on. Okay. How does it look on the IBM Cloud? So these are all the resources. So if you go to the IBM Cloud, you'll see a bunch of resources we have allocated to this project. This is your Internet of Things. You have other things like databases and Discovery Assistant. This is Watson stuff. And then we have Cloud Object Storage. So Cloud Object Storage is very key because that's where all the pictures are going to get saved. And it's very cheap cloud storage option, right? So if you send the large pictures through MQTT, it's not going to be efficient. Just store the picture. How we control it is a whole different story. What if there's a connectivity issue and all that? I'll come to it. I know that actually explains that. So you can see a lot of communication going on. This is again on the IBM Cloud. We're now deploying everything to OpenShift. So OpenShift is basically the Red Hat version of Kubernetes. So Kubernetes is kind of where everything is going, Docker and Kubernetes deployment. That's what we're doing, but we're using OpenShift, so it's stable and supported and so on. Okay, and of course, Red Hat is now IBM, so we get to use it for free. So, yeah. So now, taking a little bit deeper dive into the mechanisms, we wouldn't go through the whole complexity of all this, right? How we're spawning threads and all this. But I just kept it in there, so if someone is interested, you can come back to me later on. But you can see there's we've introduced a database and we've also introduced queues in there. And the primary reason for queuing is the instability of the network connectivity, right? So if network connections go down, it's fine, this logic will take care of it. Database, again, very important because say 2 people are scheduling and there's a schedule overlap. Which one are you going to take up, right? So there's a priority system, so even if there's a priority system, both can be of the same priority, right? Gravitational wave observation is obviously you will have higher priority than a meteor shower, right? For instance, 2 extreme ends of the spectrum. But what if you have 2 events, still it's overlapping, they have to be notified that we cannot take the picture and so on and so forth. So that's basically what that database is doing. And then there's a very simple communication. We want to put the whole thing on a Raspberry Pi eventually. So very, very lightweight Raspberry Pi, and that Raspberry Pi already has a way of killing the power if needed. So if the telescope is going, you're detecting, you're trying to stop it, you have no-go zones and all that stuff, still something happens, it touches something. So there's a ring around the telescope which has been designed now at IIT, Illinois Tech, and if it touches something, it's just going to break the power. That's it. So that's the absolute fail-safe mechanism if everything fails. Okay. Okay, observing director. So talk a little bit about this observing director. So all these events are being consumed through the event consumer. Then you go into a scheduler, then you try to schedule whatever the observations are. You filter telescopes, you do all this, and then after that, you have a bunch of telescopes that you want to cover area. So what you've realized is this SLSQP algorithm works pretty well, for now at least, for covering areas, and it's stacking up things like that. Okay? And if you, again, if you want more technical details, just let me know. Down to the code. Okay. Astronomy system. This is a way of communication with the system, and you'll see a lot of Watson services here. It's a very AI-rich sort of thing, but this can also be reused for other things. So what is Watson natural language understanding? We're using that to interpret all the intents and stuff, and then you can build models through Knowledge Studio, and then deploy those models so that you can interpret the data. So what data are we collecting? We're trying to read journals and websites and social media posts, and trying to see what information we can gather into a corpus, and then we can answer questions on astronomy from that corpus automatically. So this I put on pause for a few semesters. We'll get back to this. We want to get the core systems all working, and then we'll work on this again. The other key feature, which we did a few iterations of, is this little thing in the middle. So there's cloud annotations, which is basically a way of annotating and labeling different types of objects, and then you can categorize objects into say a galaxy, whether this is a galaxy or a planet or things like that. So if you look at it, yeah, you can tell. But for a computer, it's not that easy. So you have to train a system to understand whether the main object inside that is a planet or a satellite or star or whatever it is, right? So that's what that is doing. Okay, and obviously this all communicates to the IoT system. So all the pictures that are going in here can eventually be cataloged and put into the system. Okay. What is the future of this? So this is interesting. We're not there yet, obviously. Say someone goes to the chatbot someday and says, hey, well, what is the Horsehead Nebula, right? So it has to go through a whole process of what that means, get the array deck of that Horsehead Nebula object, then it finds some information through the corpus and all that, and says, oh, okay, amongst all these objects, okay, so this this is interesting. So it's gonna eventually ask you. So do you want to take a picture right now of the Horsehead Nebula, for instance, right? So no, it has to find what telescopes then can actually take the picture and then calculate all the filters that are needed and all that stuff to take that picture at the bottom, right? So so that is eventually the goal. That everything a human being is taking decisions for right now can be automated, and ultimately what the user wants to see is a picture of a Horsehead Nebula, right? And then after calibrating and doing all that stuff, it takes the picture and sends it back, right, with some information about the Horsehead. So that's the whole idea. And this is this researcher in IBM. His name is Jeff Peppard. This particular video, it wasn't Vimeo. Somehow it's been taken down, or there's probably a time expiry or whatever. It's a very interesting video actually. So I took out the link. If I find it, I will send it to you if you're interested. Yeah. So this is an exoplanet investigation that he demonstrated with Watson, right? So this is interesting because if you, the whole idea is pointing to an object and understanding what that object is, right? Rather than me saying or writing it down that I need Horsehead Nebula, I have a picture with lots of things, and let give me information about this thing, right? So what is this thing? It's easy for us to interpret because we have eyes and we have all these images saved in our brain, and like, oh, that's the Horsehead Nebula. Oh, this is Uranus or something like that, right? But for a computer to understand where exactly that outline of the object is not simple, right? So that is something that Jeff Keppard worked on something back on our research, and hopefully at some point we can revive that research and bring it into the network. We're also looking at communicating with a CubeSat that we sent recently. It's called Endurance. It's an 8U CubeSat. We haven't been communicating as well. We have to increase the bandwidth, and with CubeSats it's obviously difficult because now you can only communicate at certain times through ground stations, right? You can't just, it's not like internet. So we are looking into that as well in the future. There's an article we published sometime back. Please take a look if you're interested. How we worked with the students to bring this together. And not a complete project, but this is how we're moving. And a couple of other things that in the near future, in the near past, came up. One that was there was a conference at UIUC, right? And I have the link there. That was an interesting conference they had about similar idea to have a network to do transient follow-ups. Though I don't think anything actually came out of that except for this paper. And another discussion that happened over at Northwestern. So I've included those. And I think that's it. And I have some reference things you can look at. And thank you. Thanks. And if you have questions, you can always reach out.
I wanted to go back to that picture, that blue picture. I was thinking, is that a pepperoni stick, a skewer? Pepperoni skewer? No.
Oh, this one?
Yeah.
No, this. I think this is some simulated picture. I don't think this is an actual picture, right? But it's sort of showing a supernova sort of explosion, right?
So who owns the data?
Who owns the data? Whoever stores the data. At the moment, it's IBM. So yeah, it can be released. The whole idea is to have all the information released, not as just open source, but open. So that's why I call everything open, right? The project itself is open. So if you want information about the student project who's working on the project right now, you can get that information. It's truly open development. So yeah, if we, but then again, it's not just us. If say Jeff from ID, he's a professor. He's taking some pictures, right? So if he doesn't give permission for us to release his pictures, it's not right? So,
Yeah.
so yeah, there can be other issues of releasing of pictures and stuff, right? People might be doing some experiments in the future that they don't want anyone else to see, though it's an open framework, right? So those barriers have to be dealt with, right?
Have you thought about taking this architecture and applying in any other use cases, or suppose, for example, geothermal detection or weather detection? A lot of devices which are all around the world. And
Yeah, so certain things can be reused, right? So if you look at it from a high level, right, the IoT thing, this can be reused for any sort of a thing like this. So I have another autonomous car project going on with NC State. So what that does is it's a racing car. It's a small model TT02 Tamiya racing car, 1/25th model size. And we're trying to go around the track and trying to see if we can actually do race eventually, right? Right now, so we started off with the Jetson Nano, and NVIDIA has some open source stuff already. I can share with you, not a problem. So we started, that was our starting point. Initially we started a STEM program just to show kids in high school and stuff how you can train a model and so on. But it evolved to even more than that, right? So what we realized is that NVIDIA model that is out there is really not very efficient, right? So now we're looking at how we can make it more efficient, lane detections and all that stuff built into it, and then we need to have a stereoscopic vision, right? So we're no longer looking at LiDARs. So a lot of people were looking at LiDARs to detect 3D mapping, right? But you can do pretty good mapping with stereoscopic vision, right? So and that's what Tesla is doing. So yeah, it's using a similar kind of. I don't have the diagram with. I can bring up that diagram too. It will have a similar sort of environment, right? You need a proximity network. You need to connect to the internet. Once you develop one, you can reuse that code for other stuff, right?
So let me ask, I'm trying to get this over to cybersecurity for a minute. I'm imagining all of this is within the IBM global network, which is locked down very hard. But if somebody were to break in, the damage that they could do is to destroy telescopes, right?
Yes, potentially, yeah. But the device that is connected to the telescope is right with the telescope, right? So even if you send a signal, that's the whole idea behind this, right? So there's a on-prem, if you send a rogue data, right, rogue coordinates into the system, somehow you hack in and send a rogue information that can destroy the telescope, this protection module would protect you, right? So, and this is, this whole thing will be in this Raspberry Pi, which is attached to the telescope, so that you can break his telescope. But we should prevent anyone from getting into the network in the first place, right? So right now we didn't actually consider all this security aspects, but obviously, yeah, at the end of the day, when it's in production, it will have to get certified and all that, right? And if it ever becomes an IBM product, there's like hundreds and hundreds of tests and things that needs to happen. Even from a UI perspective, why certain buttons are not somewhere. So yeah, there's a lot of scrutiny and things that will happen if it's an IBM product.
Thank you very much. I think you recorded this too, did you?
Yes,
Okay, so you'll be able to provide some link that we can post on our site.
yes, absolutely.
Okay, perfect. I think dinner is served in the lunchroom, and you can basically continue discussions with Ron or anyone else during dinner. Thank you, Ron.
Sounds good. Thank you so much.
Lovely.
Thanks.
Did you enjoy it?
Yeah.
Yeah.
That was great.
The system
That was so different
itself
than anything I've ever seen in my life.
that-
Yeah.
I mean, the system itself.
I went to
doesn't-
Chile and I went to the Canary Islands and I heard about these.
But the way, yeah, individual parts are not that complicated, but the amount of stuff that is going on inside one system.
Oh, well, we can even
They're like
introduce
billions of
blockchain
small,
into this,
easy
right?
parts that
So say you want to register, so someone say, oh, I send this command, but this telescope did not
I love that
move, or
they
something,
use
right?
Raspberry
Now there's a lawsuit between the sender company and the guy who's providing the telescope, right? So
I was wondering,
that's where blockchain comes in, right? Where you don't trust each other, right? So you can have it recorded, and that's most of all the use cases. Talking about like abstract things.
Yeah.
I like abstract things because you can reuse that same concept for other things, right? So the problem that blockchain is solving is basically this distributed ledger and people not trusting each other. And that itself, we have a blockchain project with healthcare. And the whole idea can now, we are trying to apply to manufacturing. Right, the same problem, right? So a product is moving from process, so task 1 to task 2 to task 3 to task 4. So, right, so now University of South Carolina has a project, they got some grants, they want to work on that. Like, hey, so I already have this sort of there from the healthcare project, so we can reuse this ideas. That's
I didn't know I didn't really understand what your job was. Your job is so fun. Right?
Yeah, if it's not fun, I don't do the project.
Right.
able to
So much fun.
really
Like,
see the
when you were sitting here,
the
talking
big
about this, and then
difference
we worked with
between
universities,
using
and
one
then just like,
all of my projects
so much fun.
that I'm
Because this
doing
isn't the,
are mostly
and this isn't the only thing you do. You do other things besides the telescope. For
Yeah.
you do any.
like I can do
Yeah,
that
so
on
this is one of my projects. Like the car thing I was saying, that's another project.
So much fun.
So brain aneurysm is another project we're doing. So that's about detection of brain aneurysms. Which ones to operate on, right? So you can have like 20 aneurysms in your head. You'll be fine for the rest of your life, right? So there's a professor at Iowa who has a patented process in detecting, and we're trying to automate that. So
different language.
So I tried to get some more AI folks here and some more students. So I'm glad you were able to join us. So
It was amazing. Thank you so
it
much.
was so cool,
Well,
right? I
absolutely.
was so
Thanks for coming.
upset that these other students didn't come because they would have loved this.
This is true.
So I'll make
This
them
is so
watch
chat.
it.
I'm the only one.
Yeah, I'll make them watch it on the website.
yeah.
So we'll publish it.
Are we going to talk right now?
Yeah, we can go we'll have
Yeah.
dinner.
Hey,
and
we'll have some
chat
dinner, yeah.
And,
Let
I'm
me
gonna
stop
have
all
to-
this stuff,
Okay.
and then I'll
Yeah, thank you, Ron.
You keep
Hey,
saying
thank you so
you're gonna
much.
have like a